Welcome friends, Igor is here, and in this video we will discuss how to change bases in vector representations. In this lesson we will define the change of basis matrix, learn how to compute this change of basis matrix, and learn how to change the vector representation with respect to one basis to another basis quickly and efficiently by using the change of basis matrix. Let's get started. In the last videos, we discussed how to compute vector representations of elements of vector spaces and matrix representations of linear transformations. But computing these representations requires fixing bases of the related vector spaces. And the natural question to ask is this: what happens if we choose a different basis? That is, what is the effect of change of basis on these representations? This effect can be described by the so-called change of basis matrix. Suppose we have two bases B and C of the same vector space V. Then the change of basis matrix from the basis B to the basis C is defined as the matrix representation of the identity linear transformation on the vector space V relative to the bases B and C. Here is an explicit description of this change of basis matrix. This is based on the definition of the matrix representation of a linear transformation, and we see that essentially this matrix reduces to the following computation. We take every vector in the basis B and we coordinatize these vectors with respect to this new basis C. The results of these coordinatizations become the columns of the change of basis matrix. Here is an immediate application of the change of basis matrix. It allows to transfer vector representations in the basis B to the vector representations in the basis C via matrix multiplication. This commutative diagram will help you follow through this proof. To compute the vector representation of the vector V relative to the basis C, first let's observe that the vector V is equal to the identity linear transformation on the vector space V applied to the vector V. Now we are going to apply the fundamental theorem on matrix representation. And the last step is to recall the definition of the change of basis matrix as a matrix representation of the identity linear transformation. Next, let's suppose that we have a vector space V and again two bases B and C of this vector space. Then the change of basis matrix from the basis B to the basis C is a non-singular matrix, therefore it is invertible, and its inverse as a matrix is a change of basis matrix from the basis C back to the basis B. Once again, these two commutative diagrams will help you understand what is going on here. The whole proof is based on a simple idea. The inverse of the identity linear transformation is the identity linear transformation. This means that the matrix representation of the identity linear transformation, which is the change of basis matrix, is invertible as a matrix, therefore it is non-singular. Also, the inverse of this change of basis matrix, which is the inverse of the corresponding matrix representation, is equal to the matrix representation of the inverse linear transformation. We have proved that taking the inverse of a linear transformation is equivalent to taking the inverse of its matrix representation in one of the previous videos. But then the inverse of the identity linear transformation is itself. And this matrix representation is the change of basis matrix from the basis C to the basis B. I am going to illustrate these ideas with the following example. Our vector space is column vectors of size 3, and we are going to take two bases. B is the nice basis, it consists of standard unit vectors, and we take some other basis C. I will compute the change of basis matrix from the basis B to the basis C, then I will compute the change of matrix from the basis C to the basis B. We will see how they are related and how they can be used to compute vector representations in a different basis. To compute the change of basis matrix from the basis B to the basis C, we need to take each vector in the basis B and then coordinatize this vector relative to the basis C, and then conversely for the change of basis matrix from the basis C to the basis B. So let's start with the computation of the change of basis matrix from the basis B to the basis C. The first column of this matrix is the coordinatization of the first vector in the basis B relative to the basis C. This coordinatization is a column vector of size 3 whose components satisfy the given equation. Recall that to coordinatize a vector relative to a basis means to decompose this vector into the linear combination of the basis C in this case, and the scalars in this linear combination are then used as components in the coordinate vector. But this equation can be thought of as a linear system in the variables x1, x2, x3, and this linear system can be represented by this augmented matrix. The second column of the change of basis matrix is the coordinatization of the second standard unit vector relative to the basis C, and once again, the computation of these coordinates involves solving a linear system represented by this given augmented matrix. Same idea for the third column of this matrix. It is the coordinatization of the third vector in the basis B relative to the basis C, and these coordinates are the solutions to the linear system represented by this augmented matrix. So let's summarize what we discovered so far. To find one column of the change of basis matrix, we need to solve a certain linear system. But when we write all these linear systems next to each other, you recognize that they all have the same coefficient matrix. They only differ in the vectors of constants. Moreover, the coefficient matrix is non-singular. Why? Because its columns form a basis C of the vector space C3. Therefore, instead of solving these three linear systems separately, we can solve them all in one single go by reducing this one large matrix. The left part that corresponds to the coefficient matrix will reduce to the identity matrix, and the right part, which corresponds to the vectors of constants in the linear systems, will reduce to the corresponding solution vectors. This computation allows us to see what the vector representations we're looking for are, and we put these columns together to obtain the change of basis matrix from the basis B to the basis C. Next, let's compute the change of basis from the basis C to the basis B. For this, we have to take vectors in the basis C and coordinatize them relative to the basis B. But the basis B consists of standard unit vectors, so these coordinatizations are easy to compute because coordinatizing relative to standard unit vectors is simply the identity linear transformation. So we obtain the change of basis matrix from the basis C to the basis B with little effort. Also observe that the change of basis matrix from the basis B to the basis C is exactly the inverse of a change of basis matrix from the basis C to the basis B. We proved that this holds in general, but this is just an illustration of this fact in this example. So why do we care about these change of basis matrices? Here is one application of these matrices. In this example, it was easy to coordinatize vectors relative to the basis B because it consisted of standard unit vectors, so it was an identity linear transformation. But coordinatizing vectors relative to the basis C was much more difficult because it required solving linear systems. Here is an illustration. Suppose we have this vector 2, -1, 9, and we would like to coordinatize this vector relative to the basis C. For this, we need to find the scalars in the linear combination of the vectors in the basis C that is equal to the given vector. And computing these scalars requires solving a linear system with this augmented matrix. We can reduce this augmented matrix, and this will give us the unique solution to this linear system, which corresponds to the components of the coordinate vector relative to the basis C. But we could have obtained this presentation much more efficiently by using the change of basis matrix. We proved that coordinatizing relative to the basis C is the same as coordinatizing relative to the basis B and then changing the basis from B to C which can be realized via multiplication by this change of basis matrix. Why is this computation more efficient? It's because it is easy to coordinatize relative to the basis B. There is no linear system to solve. We computed this change of basis matrix, and now all we have to do is to perform this matrix vector multiplication. This results in the desired vector representation of our given vector relative to the basis C. Now, here is a question for you to ponder. Does this computation remind you of something else? Please pause this video for a minute and think about this before I give you the answer. The analog of this computation that we saw earlier is solving linear systems where the coefficient matrices are invertible. To solve such linear systems, we could find the inverse of the coefficient matrix, and then the solution vector would be the vector of constants multiplied by the inverse of the coefficient matrix. This is essentially the same thing that we're doing here. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss what happens to matrix representations of linear transformations when you change bases of vector spaces. I will see you later.